Hey guys, my name is Biswa. I'm from Meta. Welcome to Presto-on July 2022. I'll be talking about Presto in the context of shared foundations of open data lakehouse analytics. This is a kind of a lot of buzzwords. So let's first talk about what these things mean and how they fit in. So when we think about the data world today, uh, we see two types of trends. I would classify them as usage-based trends and environmental trends. Now, the usage-based trends are kind of fairly obvious, I think. We have an exploding amount of data. Machine learning is getting more and more integrated with analytics. Privacy and security are becoming more and more important. People need access to fresh data and really fast data. Analytics is being exported to the user. Data models are becoming more complex, or queries are becoming more complex. The environmental trends are somewhat different. They are more dictated by how the hardware is progressing, how the cloud is progressing. So some examples here, uh, storage disaggregation is non-negotiable these days. Horizontal scaling is non-negotiable. Moore's law is dead. Elastic compute has to happen if you want to deliver good price performance on the cloud. More and more is no longer about the capex or the cost of the hardware, but also about the cost of the power required to run that hardware. We are no longer thinking about local optimizations, but rather globally across our entire data stack. And finally, engineering efficiency is becoming more and more important because as organizations start realizing that we are spending a ton of money of engineering and we cannot really keep scaling engineering as the data scales. We have to find sublinear methods of scaling ourselves. So open lakehouse analytics has kind of emerged as a common pattern. I think this term was probably coined by uh, Databricks initially, but this is a fairly obvious pattern and this is actually fairly common. Uh, Basically, this is characterized by two main things. One is direct data and metadata access. The other is diverse set of applications running on the same data directly. So by the first, we mean all the data is stored in open file formats. The metadata APIs are open. So different engines can all directly access the same data using the same metadata APIs, which obviously means that the storage needs to be disaggregated from compute, as we have talked about. And then this results in a diverse set of applications all running on the same data. So we have batch processing, interactive processing, stream processing, ingestion, machine learning, all running on the same data. So let's agree that this is roughly what a open data lakehouse uh, means, right? And I think you can draw a contrast to, the old databases which had co-located storage and compute, and data could only be accessed through their SQL APIs, or even newer data warehouses such as Snowflake, for example, where yeah, the storage is disaggregated, but the file formats and metadata APIs are not open, so you have to read it through the Snowflake APIs. Contrast that with files directly stored as ORC files on S3. So Presto can read it, Spark can read it, and so on. Right? Now, at Meta, we have been following the so-called open data lakehouse architecture for a while now, and that this is roughly what it looks like. We run a ton of services, mostly on the web. These services result in data being read and written to databases, and they generate a ton of logs. These logs are further processed by stream processing, and then these databases and logs are ingested into our warehouse. The warehouse is open. It's essentially a set of DWRF files, which is basically a variant of ORC. The metadata is essentially an extension of Hive MetaStore. And then on the same data, we get ingest running, producing the data, batch processing, modifying the data and producing new data, interactive queries running fast analytics on this data to power dashboard. This is obviously where Presto shines. And then finally, we have got a bunch of ML training happening on this data. There are some other processes that I've not mentioned. For example, we also have graph queries running on this data, but I wanted to keep this diagram simple just for illustration purposes. And the blue arrows and the blue boxes are essentially processes that need to transform the data in some way. Like ingest is, for example, converting data from row-oriented to column-oriented. Stream processing is doing continuous joins on this data and so on. Like ML training is doing some transformations on this data and feeding it to our PyTorch model trainers and so on. Presto-Spark similarly. Now, the problem is that even though fundamentally a lot of these blue boxes are kind of doing the same thing, if you look at it, there is a huge amount of fragmentation. None of the aspects of these blue boxes, the processing boxes, actually share anything. So they have different SQL dialects at the language layer, different ways of executing distributed execution, different shuffles, different resource management, different eval engines, different caching strategy, uh, different ways of accessing data. Like we use different languages. The ML stack uses C++, the Presto and Batch, Presto and Spark use Java, Xstream, our stream processing against uses C++. They all have different engines, different libraries for reading and writing ORC files, or reading from scribe, or parsing JSON data, or whatever. And this clearly creates a ton of problems. A, we don't have any standardization of the languages and the APIs. This creates a huge amount of redundant engineering effort for our engineers. And C is that it just makes any kind of innovation very difficult and slow. Like for example, adding a simple codec to ORC might be several months of effort. So what is the impact here? The main impact here is poor innovation velocity and poor user experience. But what can we do about it? And this is where shared foundations comes in. What we can do about is defragment the stack, and more importantly, build shared components. In other words, we need to acknowledge that, hey, one solution does not fit all. So we actually do need different engines. Like Presto itself cannot solve all the different problems of streaming and ML and batch. But what we can do is build shared components, taking the best of breed, and make all of these different engines use them, so that you do the work once and it benefits everybody. And let's talk a little bit about how we have gone about doing it and what are the different aspects of it. So let's start with interactive analytics, because that's where Presto fits in. So what did we do? We initially had non-disaggregated co-located storage for fast access. This was our old Raptor engine, and we had some other smaller engines like Kubrick and so on. And then we had like suboptimal distributed plans. We had node execution performance issues and so on. So we started by disaggregation, but disaggregation means your query is slow, which means we had to build RaptorX, which essentially introduced new caching methods, new affinity methods. Similarly, for suboptimal distributed plans, Raptor had its own metastore, but we don't want to disaggregate don't want the co-located metastore. So we had the Hive metastore, but in order to meet the performance needs, we had to enhance Hive metastore to have richer metadata. We had to build new optimizer tricks. We had to build more caching of the metadata and so on. And as a bonus of that, we got richer partitioning. We got features like materialized views that could be used across engines. For node performance, we essentially rebuilt the whole eval engine from scratch in C++, and this is how Velox was born. And one of the nice side effects of this is that because Velox is C++, it could actually be used in the Java engines such as Presto and Spark, and also in the C++ engines, which meant that it became far easier to get us moving towards dialect conversions. Now, if we move to batch processing, going from the previous example, now we can reuse the node eval engine Velox, and this accelerates the batch performance significantly. Then again, the richer metadata and optimizer we had built for interactive can actually be equally applied to improve the distributed plans for Spark jobs. So we built Sapphire. We'll talk about that a bit. Cluster scaling and utilization, we had to build Fireball and Pack. And then finally, for reliable and distributed execution, we said, hey, we already have Spark. Why don't we take Presto's engine and take Velox and run it inside the Spark engine? And we essentially built Sapphire, which basically is Presto-on-Spark. And one big benefit of that was now the user can use the exact same dialect to run both interactive queries and batch queries. And then real-time data. This essentially has two parts, the real-time ingestion and the stream processing. Similar thing, we said, hey, we could use the same engine to build these vector conversions, like from row-oriented to column-oriented, or to apply projections and filters when we are ingesting data. In fact, we ended up embedding Velox in our ingest stack and in our stream processing stack, Xstream. And this resulted in a lot of benefits. Not only is it more efficient engineering-wise, but it also ended up helping with dialect consolidation between batch, streaming, and interactive. Similarly, it allowed the user to write real-time transformation rules while ingesting data into the warehouse. The richer metadata layer that we built in Hive Metastore allowed our ingestion team to build richer partitioning strategy into the ingestion layer itself. So as you can see, once we get into this open Lakehouse architecture with disaggregated storage and metadata and create reusable components around it, this is the important bit. You can now leverage these components that we built for one type of analysis into other types of analytics. And finally, let's talk about machine learning. We found out fairly early on that, hey, machine learning, the existing file formats are not particularly suitable for this very large feature sets and huge metadata overheads that come with it. So we are building our own file format. It's called Alpha. And one of the nice things about that is that we found out that this actually helps also in analytical query workloads. Alpha actually significantly accelerates analytic queries as well. So it's not just about machine learning, even though initially it was targeting machine learning. Similarly, we found that the C++ engine Velox that we had built for analytics actually can help ML training a lot, because ML training often uses a fair amount of pre-processing to filter project and otherwise massage the data before converting them into tensors and feeding the PyTorch training process. Interestingly, the same set of functions that they use during this time can often be reused at inference time and also during feature engineering time. So now, once we started optimizing Velox for very low latency queries, it turns out that this optimization could also be used to embed Velox in our inferencing engine. That's what we are doing today. And this is actually making our ML engineers' jobs a lot easier. Finally, the rich metadata API that we had bought actually turns out to be very useful for creating smarter layouts and partitioning for machine learning data. This makes the ML data much more efficiently stored and much more efficiently used. This is actually a huge deal because, as we know, ML data is growing much faster than analytical data. So we suspect that soon ML data will surpass analytical data by a significant amount. So these optimizations are going to be even more important in the ML world. So just to wrap things up, I think the important takeaway, if there's one takeaway I want to say, is that building shared foundations is really important. Open lake houses are not just about the core principles of storage and metadata disaggregation and the ability to use the same data for diverse workloads, but it is equally important for us to share as much of the code as possible in the process, because this allows us to accelerate our innovation a lot faster, and it allows our users to create a much more cohesive end-to-end experience across ingestion, batch processing, interactive processing, stream processing, machine learning, and beyond. For example, we are actually now experimenting with putting Velox in our OLTP distributed stack as well. So thank you. And finally, yes, we are still hiring the right people. Please talk to us offline. We'd love to hear from you. Thank you.